Good afternoon, everyone. Today we will have a presentation on gallium nitride based semiconductor devices, their simulations, and we will look at various fields where the device modeling lab does its work. The introduction will be given by Mr. Naveen Sundar Siva. I will take over, talk about some plasmonics and certain solver-based approaches. Kaleyarahan will talk about Spintronics-based applications of these kind of devices. I invite Mr. Naveen to start the presentation.
Good evening, everyone. I'm Naveen. So today we can discuss about an overview of gallium nitride based devices. Okay. So there are numerous of silicon based devices out there, but we are focusing on GaN based devices. Why we focusing on GaN based devices? Because it has certain electrical properties superior over other commonly used semiconductors such as silicons. So, and the homogeneous structures, homogeneous elements like silicon, homogeneous
No, I think here.
Homogeneous materials needs some doping, but in heterostructures there is no need of such dopings. The electron is formed without the doping due to its polarization and the discontinuity in band. So the band discontinuity and the polarization is due to its crystal structures. So let us discuss about crystal structures of diamond and rosette crystals. So in diamond or FCC, it's face-centered cubic, and rosette structure are hexagonal structures. In rosette structure, there is a non-centrosymmetric inversion will be there. So there is a piezoelectric polarization will happen. But in the diamond structure or zinc-ion structure, there is inversion symmetry structure. So there will be no polarization. Piezoelectric polarization happen there. So these are the zinc platinum structure and the rosette structure. So now just get into the material properties why we moved into the GaN based devices. So the silicon have the electron mobility of 1350 centimeters square per volt per seconds, and GaN have 1500 centimeters square per volt per seconds. So, and the breakdown electric field is almost 10 times over than silicons, and thermal stability is over 800 degrees Celsius, which we can use in high voltages applications. And the electron saturation velocity is over 2.5 into 10 to the power 7. So, and there is a polarization will happen in GaN materials. So, not only just with the GaN, we can make the certain mobilities by including the algan material or overthrowing of algan over GaN. We can get the heterostructure which forms a potential well which populates the two-dimensional electron gases. So now it can be achieved through the epitaxial growth of material algan over GaN. So this can be achieved through molecular beam epitaxy, liquid based epitaxy, and vapor based epitaxy. So these are the liquid based and vapor based and chemical vapor epitaxis. These are all well known. And while growing electrostructures, there will be a stress and strain created in the electrical structures. So that are the structures. There are various structures of heterojunctions which forms a staggered gap, static gap, and a broken gap. So static gap is what ion GaN devices are made of. So the conduction band minimum and the valence band maximum of one material is lies between the other material forms a static gap. Okay, so here you can see the GaN material is over the wide band gap and the ion material is ultra wide band gap here. So we talk about the polarizations. So there are a lot of polarizations, but here we just discuss about the spontaneous polarization and piezoelectric polarization. Spontaneous polarization is an inheritance property. So there will be a polarization occurs without any external field or any mechanical stress. But in piezoelectric polarization, if the polarization happens due to the stress when growing epiaxially. So these are the structures of polarization, spontaneous polarization, and here you can see there is a stress here, so there will be a polarization happening due to the atoms here. So while growing electrostructure, the alkyl GaN material can be formed into two types. So G-phase polar and N-phase polar. So irrespective of its growth type, the two-dimensional electron gas will form in GaN interface. So now let's move into the formation of two-dimensional electron gas. What is two-dimensional electron gas means? It's an electron channel that confined in two dimensions. Okay, so here this is a alkyl material. It's a alkyl GaN interface. The positive polarization and the other alkyl GaN interfaces. So and due to the polarization charge, the band gets triggered. So and this is surface Newman state. What is the surface Newman state? Is damping bonds of the devices which populates the two-way layers. So the electron from the two surface states get hops up into the conduction band of alkyl material and to its slope it bends due to the discontinuity in band. So and the electron flows from the conduction band of alkyl to GaN interface. So this forms a two-dimensional electron gas, which is here. This is a potential well, so where the electron gets accumulated here. So and there are also some factors that affects the two-dimensional density. So which means the alkyl proportions the composition of aluminum in alkyl varies two-dimensional populations, and the thickness of the alkyl will also in directly proportional to two-dimensional electron gas. And doping the alkyl, we can achieve high two-dimensional density, but it can lead to the some scattering which makes the mobility deviate. So here you can see that. So this is the alkyl GaN. So here this is a two-dimensional. This is a Bernoulli electron, this is a conduction band, and this is a valence band. So the two-dimensional electron gas will be here. So the electron gets accumulated in this area. This area. So we just see that alkyl GaN materials have a intrinsic property of two-dimensional electron gas, which we get the normally on ends. So here the channel is formed in the GaN region. Here, so this is a band diagram of normally off ends. So this is the two-dimensional electron gas is formed here. So and this is the IV characteristics of normally on ends, which you can it's a -1 volt of threshold. So, and there is a normally off, hence why we go going for normally off, due to its safe operations. So, here it's a equilibrium. So, 2H is depleted under the gate. So, the 2H is depleted due to the P alkyl. So, sorry, PN material, which has a donor acceptor atoms, which deposits the electrons in the channel. So, we achieve the channel division under the gate. So that's the equilibrium. And when we bias condition, the threshold voltage is achieved after nearly a 1.5 volt. So until now we just see the basic operations of HEMTs and how the two-leg is formed. Now we are getting to the second order effects of HEMTs. So there are the second order effects of HEMTs are traps and current collapse and self-heating effects and dynamic alarm and gate leakages. And here we just see the gate loses stability due to the electron which passes through this GaN and get into the gate metals. So normally the Schottky diode will be happen, but due to some high voltages, the electron is in the channel get linked to the PN and get into the electrode of gate. So that pushes the gate reliability. So that should be mitigated. So and there are surface donor states at the GaN. What we just previously talked about, the tangent bonds of the devices makes the surface donor states, and there are some traps which holds the electron or lose its electron that affect the devices. So and this is the hot spot region. So when the high voltage is applied, the first semiconductor is get electric field distributed at the PN area. So the peak electric field is get over the substrate. So that increases the heat of the devices, and which leads to the electron high energy of electron and it leads to the gate leakage. It's also called as a current collapse method. Okay. So these second order effects can be mitigated. So just before that we just see that what are the traps interface, the every material when in IC application there will be a error which occurs in every electrical board. There will be interface traps between GaN and GaN substrate and GaN channel and GaN barrier and others vacillation layer. So these second order effects can be mitigated through various structural modifications. So here we just introduce aluminum nitrate to reduce the interfacial traps which occurs in GaN interface. So and which improves the polarization and reduce the scattering in channel. And this is feed plate techniques, which is a better extension of the source or drain or gate metal extensions that reduces the electric field modulations. I mean which distributes the electric field. Last time we talked about the hotspot region, so that will be get distributed. So that improves the breakdown electric field. The breakdown electric field, the material gets breakdown after certain voltages and high voltages. So if we have a breakdown voltage of 500, by using this offset material, by implementing feed plate techniques, which increases it to 600 or 700 volt material breakdown techniques. So these can be mitigated. So and the dynamic power is the devices of we are using transistor and AC circuit. So in offset we are ramping the drain voltage is high. So that gets some trapped or vacancies defects in devices which trap the electron or force, which makes the current collapse. After the gate is biased, those electrons will not respond immediately. So that is called as gate or drain lag. So and there is a screening effect. We just talked about the These surface overlaps the material on the devices so that can be mitigated through the linear extensions. The same thing which we limited the channel. So by extending that we can achieve the surface charge screening, which because the electrons are giving to traps. So the field modulation will also be mitigated. The same products and the dynamic causes the lag of brine and gate will be also mitigated. So these are the basic operations and these basic operations of things. And now I will hand over the session to the Srinivas Ramanujan who give the detailed current transport equations and its plasmonics based devices also.
Let's have questions on the last one. We have two more presentations.
இன்னும் மணியாக்கு யாருமே வரல. இல்லை 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 அப்போ இதில் வால்யூம் கேட்காதுல்ல.
அது எப்போ அது ரெக்கார்ட் பண்ணலாம் இருக்கு. ஹலோ okay. So thank you Mr. Naveen for your presentation on basic HEMT operations and certain physical concepts that relate to the formation of electromagnetism and network of that sort. I'd like to pivot a little bit and talk about a specific application based on surface plasmon polarities. So, when you look at Naveen's presentation, the device has three terminals: source, gate, and drain. Source is where the electrons get injected. Conventionally speaking, could be the program. Gate is basically what controls the electrons in the channel. And the drain is where the electrons get subject or where the current goes. Depends on what you define. Generally, the source and drain are interchangeable. One of the like I said, the gate electrode is what controls the electrons in the channel, which means that it controls the conductivity of the device, it controls the output current, it controls the threshold voltages, it controls where exactly the device switches from on to off state and all those things. One of the applications of the device is in terahertz detection, where a terahertz pulse is shined upon the gate electrode, and this causes certain oscillations on the surface of the gate. These oscillations are called surface plasmons. These surface plasmons they cause a perturbing potential which affects the transport of the electrons in the channel molecules. So this is just a basic illustration of what a surface plasmon looks like. So I'm shining light on this particular surface, which is a metal surface. The requirement is that the dielectric of the metal is frequency dependent, the dielectric constant. So once we have that, forget about the equation. I'm just going to talk qualitatively. So the dielectric of the metal surface, it is frequency dependent. Depends on the frequency of the define what the frequency of the propagating plane wave on the surface is. Let's say I just illuminate the surface of the metal with light, and at certain frequencies I will see propagation of electrons. At certain frequencies I'm going to see a reflection. At certain frequencies I'm going to see a dissipation or an absorption. So I'm going to the equations. This graph basically shows the feedback two different metals, namely gold and silver, they detect. And as you can see, for silver, the incoming wavelength is around 350 nanometers. It seems to detect it very nicely. But as gold is concerned, around 525 nanometers, but the detection is not that great. I'm going to show you some simulation results, and then I'll actually pivot to device equations. So this is a simulation that we did on console. We have a silver layer, we have an add layer, and I'm going to initialize all the material parameters at the beginning. And what I'm going to do is, I'm going to initialize this particular side of the device as the input port, this side of the device output port, meaning that the electromagnetic radiation comes from here to here, has an interaction on the surface, and leaves from the other surface. So this is what the mesh looks like, the rudimentary mesh. So this is my electric field distribution at around 370 nanometers per second. I'm seeing some kind of standing wave patterns. This is what we expect to be an ideal requirement for us to be able to sense in terahertz applications. I played around with the frequency around 340 nanometers. Just reduced it by 30 nanometers, and suddenly the whole thing vanishes. I just see some kind of accumulation at the input side, whereas it doesn't propagate to the output. This is what the reflectance and the transmittance and all this is, right? This is supposed to be ideal. The total reflection, the reflectance and transmittance cross the absorbance at the operating frequency of the device, which is around the wavelength of which is around 370 nanometers. This is my electric field mode at the input port. Right at this is the junction of the metal and the iron. I see a very high spike. At the output port, I see the exact same, which means that there is very little signal loss at this particular frequency. So how does this apply to HEMT? This is where this comes in. This is my gate electrode. I'm going to shine light on this. This causes a perturbing potential. This is my channel. So the perturbing potential on the gate electrode, which is caused by this particular pattern on the surface, this is going to affect the electron population in the two-dimensional channel. And we solve the electron transport model as well as the Maxwell's equations simultaneously. So we have an FPGA solver, 5 different time domain solver, and we solve electron transport equations. For this particular case, we actually need to do a hypothetical model. I'll explain that. So let's look at some basic electron transport models. So this is what the overall thing looks like. So the electron structure lattice dynamics. Basically, we need to calculate the band structure of the device, the equilibrium band structure of the device. We use various different abstractions, levels of abstraction, depending on the simulation complexity of our transport equations. For example, if I'm using a quantum solver, I probably have to use density function and 3D based band structure calculations. If I'm using a Monte Carlo based approach for the Boltzmann transport equation, I probably use a type binding or an empirical superpotential. He probably works on this. Islam come together to define what is called as a device simulation. So I get the band structure, I calculate I solve for the lattice, I solve for the electron transport, I solve for electromagnetics. All these three things come together to define a device simulation. So these are the levels of abstraction. The compact model we use in a circuit level simulation. We have decent models, and we have PDK, some of these things, which use data from device modeling. They abstract it to a circuit level as an input-output characteristic, and then they use that for circuit level simulations. The next level abstraction is a drift diffusion approach. Let's say that this tile is actually my lattice. I am an electron. I'm traveling through the tile. I'm traveling through the lattice. Every single point on the tile is a location of an atom. So I'm going to sense, once I start moving, I'm going to sense some kind of potential. That potential is going to obstruct or make me scatter and make me move in a different direction. Those things. Those are solved by the drift diffusion equations. There are two ways in which two reasons the electron propagates on the lattice. One is a potential difference, which causes the drift of the electrons. So once we have an electric field, the electron experiences a force, and that force makes it propagate. That's called the drift model. A diffusion is where I have a higher concentration of electrons here, a lower concentration over there. According to Fick's law, the electron tends to move. So from higher concentration to lower concentration. That's a diffusion. So this is what we call as a classical approach to modeling devices. The next level of abstraction is what we call the moments of the Boltzmann transfer equation, where we also include the energy balance equations, we include second order effects, we include some quantum corrections and all those things, where the hydrodynamic and energy transport approaches come into picture. We consider the electrons as, let's say, fluid set of particles. The fluid set of particles either moves according to laminar flow model or turbulent flow model, depending on the energy imbalance or the energy balance, which is defined or which is solved by the energy balance equations. We include those equations to the drift diffusion approach and modify it, define what is called a hydrodynamic approach. The next level to that is the solution of the Boltzmann transfer equation. This is a far more complicated problem where we will look at different types of scattering events, different types of perturbations. We have different levels of approximations. One of them is the multi-based simulators, where let's say I have 10,000 electrons in one particular area of the device. I will statistically try to solve for all those particles. I will say, let's say I am an electron, I travel from here to here. This is my free flight time, what I define it as. And then I have what is called a scattering table, which consists of all kinds of scattering events, and I will go fetch a scattering event from the table, and I will say, this is my initial momentum. The scattering event happens, probability of this scattering event happening is this. The code will basically take a decision whether a scattering event happens or not. I will calculate the final momentum. I go, let's say, over here, free flight time goes here, and then scattering happens again. Let's say I go here. It happens like that. And I statistically solve for all those particles for an extended period of time and try to arrive at some kind of a polynomial regression, which will give me the overall transport of electrons in the device, in the lattice. And this is a multi-parallel approach. The more complicated ones, which are more they have higher simulation complexity, or the non-equilibrium Green's function approaches, where we try to solve the Schrodinger equation directly, or we have a different kind of approach where we have the Wigner function-based approaches, where we say that I'm going to try to solve for the position and momentum of a microscopic particle cannot be accurately calculated at any given time. The reason being that the position and the momentum operators are basically operators of the wave function that alter it simultaneously, meaning that they exist in two different dimensions. So we end up trying to solve for the Wigner equations in what is called as a phase space, which is a 7-dimensional space with 3 position coordinates, 3 momentum coordinates, and a time coordinate. We go all the way to t equals negative infinity, and then we try to iteratively solve to current particular time, where each time step has a dependence on the previous, on the events of the previous time step. So this is considered to be an extremely difficult problem to solve, and as you can see, the drift diffusion approach will probably be accurate when it comes to devices that are in the micrometer region. The hydrodynamic approach will be sub-micrometer region, and the Monte Carlo approaches will be more suitable for devices with channel lengths that are in the nanometers, and the quantum approaches are generally used in quantum dots and to simulate what is known as a Coulomb blockade and different kinds of quantum systems that require many particle interactions. Generally, we don't solve for many particle interactions in the other regimes. So I'm going to skim through all the equations. I'm just going to talk qualitatively. So we start out with Maxwell's equation. We apply the divergence operator to arrive at what is known as the continuity equations. Basically, these are first order differentials which will be solved using we start with the steady state Boltzmann equation, Boltzmann transport, where we have relaxation time approximation. The relaxation time approximation is one of the more coarse approximations that are applied to these kind of systems, where we say that once I apply a perturbing potential and move the system from equilibrium to non-equilibrium state, I'm going to say that it takes a certain amount of time to come back to equilibrium. So basically, I have a system, I disturb it with a potential or an electric field or an electromagnetic field. It goes into non-equilibrium state, and then it takes a certain amount of time to correct itself, come back to its original equilibrium state. And that is what we call as the relaxation time. We apply it to the Boltzmann transport equation. We multiply with the velocity, the drift velocity, and we integrate the ruler. To arrive at the final expression for the density, which looks something like this. We don't need to worry about what this is. And this is the expression that we get. And then we apply what is known as the Einstein's equation, which says that the diffusivity constant divided by the mobility. The mobility is the ease with which the particle moves through the system. That equals the kT divided by the charge of the particle. KT is Boltzmann transport, the Boltzmann constant multiplied by the temperature. So we arrive at this. This is what we call as the storage coefficient, and we plot the current density for the low field regime, high field regime, and a distribution where we say that it's in the high field, but most of it gets transferred to the lattice, meaning that every atom in the lattice is going to keep vibrating. So once I have an electron, it's going to interact with an atom in the lattice and make it vibrate a little more or a little less depending on the interaction. And I'm going to say that for the last case, this thing is going to, most of the energy gets transferred to the lattice rather than the electron. The complete drift diffusion model looks something like this. We have the current equation, the continuity equation, and the Poisson equation. The Poisson equation is used to calculate the potential. The continuity equations are what gives the continuity, make sure that there is charge neutrality, make sure that all the particles that we set out to simulate are accounted for, and the current equation is what actually gives you the current density. So all these equations are simultaneously solved in order to arrive at an accurate solution to what we expect would be the physical behavior of the device. we have a mesh. Mesh is basically where, let's say I have a whole area which I need to simulate. I cannot simulate it continuously, so I discretize it. I discretize the space, I discretize the momentum, and that's what makes me come to what is known as a mesh. I'm going to solve for all these potential, the current density, the drift velocity, and all these values at each of these points. And the distance between those 2 points is what gives the bottleneck for the ease with which the simulation actually converges. And this distance is generally required to be around 2 orders of magnitude, 2.5 orders of magnitude of the Debye length. We'll define what the Debye length is in some time. So Debye length is basically a screening length of the, let's say I have a perturbation here. How far does the perturbation actually get sensed? That's the measure of that is the Debye length. Let's say I am a phonon that's vibrating. How far is my vibration sensed? A measure of that is the Debye length. Let's say these are what is known as the quasi-Fermi level approximation. We have a non-equilibrium system where we cannot really define what a Fermi level is. A Fermi level is supposed to be at the level of equilibrium at which at least half of these are coordinated. So once we attain non-equilibrium, we cannot define a Fermi level, which we generally use as a reference state to calculate much of our electron transport problems. Therefore, at the quasi-Fermi level, we use these kind of numbers. N is the electron concentration, P is the hole concentration. And we have, so these are basically the Debye length, that's the expression for it. The thermal voltage. This is the free flight time that we can maximum simulate. So we then move to what comes known as boundary conditions. So we talked about the mesh. Each point in the mesh interacts with its nearest neighbors. What happens? The number of nearest neighbors changes. Right? When that changes, the software needs to handle things differently. So for the boundaries, we have contacts. Among contacts, we have ohmic and Schottky contacts. We have contacts where only voltage can be applied. We have interfaces. We have artificial boundaries and all those things. We'll talk about that. This is what the device will actually look like. We have this is a BJT, that's a MOSFET associated right with an interface of collector. This is actually the mesh. All the intersections in this particular device is where the solver actually goes and solves. So these, wherever we have interfaces, wherever we have certain dead ends and all these things, is where we are. For, let's say, a voltage controlled ohmic contact, we apply what is known as a Dirichlet boundary condition, where we apply a certain voltage, and that voltage has to be kept. It's a constant voltage, and that will basically drive the next. Let's say, this is where I have the Dirichlet boundary condition. This points over here influence the value here, but this value will influence these values. That's all it means. Then we have what is known as a Nyman boundary condition, where I have points here. This is my boundary, but I also have points here. Values here will have an influence on the values here. That's what a Nyman boundary condition means. Current control will have what is called an integral boundary condition. Then we have, these are electron density units. These are what are called Schottky contacts. For Schottky, when we calculate potential, we apply the Dirichlet condition where we say this is my potential. But when we calculate current, we apply what is known as Neumann boundary condition, but this can actually change. This is basically the same. Then we have interfaces. For each interface, depending on the type of interface, the boundary conditions will be defined. So these are different kinds of boundary conditions, factor nodes and all those things. We don't need to go into the technicalities of this. We look at carrier action and try to finish in the next 5 minutes. We have the drift process. I already explained what that is. We have an electric field, the electron gets pushed. We have the diffusion process. concentration gradient drives the motion of the electrons, and we have generation recombination. What that means is that each lattice site is going to have a bunch of bound electrons, and those bound electrons will be excited, or excited electrons will come and occupy certain open states there. Those are generation recombination. The drift process looks something like this. Is equal to QE. Then we have a high frequency, lower frequency limits, and this is what basically looks like. Tau m is the drift time. So for each tau, we're going to say the electron drifts in. And then I look at the boundaries, I look at other things, and basically calculate what happens. So depending on whether I have energy relaxation or momentum relaxation, the type of drift movement will be basically. What that means is that when I calculate the motion of the electron, do I focus on the kinetic energy or do I focus on the momentum? When we look at this from the outside, one would say that p square divided by 2m is the kinetic energy. They are both the same. But when we also consider scattering processes, this has a different effect. So generally, for turbulent flow, we use the momentum relaxation. For laminar flow, we use the energy relaxation. Okay, so now we look at what's called the velocity overshoot effect. This region is where the device reaches steady state. Before reaching steady state, we have intervalley transitions and intravalley transitions, where suddenly the electron will experience a surge in motion. Surge cannot be calculated by a solver. So here we need to apply certain different kinds of functions and different kinds of directions which will show the velocity of mobility. Various factors affect mobility. Generally, the Matheson's rule is what we use to calculate the effective mobility in the device. These are all the factors: ionizing purity, neutral purity, acoustic phonon, non-polar, polar, piezoelectric, all those kinds of things. Using the Matheson's rule, we calculate what the effective mobility is. So this is what the mobility versus doping concentration looks like for different kinds of simulations. So as we increase the doping, the mobility is supposed to decrease. And then we have the diffusion process. Higher concentration here, lower concentration here. Balance. So these are the equations for the diffusion process. And these are the different stacking mechanisms that we need to account for. We have the defect stacking, where I have a crystal structure, and the structure is not completely periodic. It has a defect, and those defects have its effects. So we have crystal defects, impurities, and others. Impurities can be ionized or neutral. Then we have the carrier-carrier interactions, where I have 10,000 electrons. These electrons are going to interact with each other. Those interactions are generally not modeled in classical and semi-classical model solvers. Then we have the lattice scattering. These are completely purely phonon-based scatters. We have acoustic and optical phonons. What that means is the lattice vibration, if the frequency of the vibration is extremely high, we call it an optical phonon. It's going to interact with light. If the frequency of vibration is smaller, we call it acoustic phonons. These can be intervalley or intervalley. What that means is within the lattice, we have valleys. How do I explain this? Okay. The energy of the electron is going to be parabolic along the lattice. Basically, the energy is h bar squared k squared divided by 2m. It has a quadratic dependence on the wave vector or the momentum. So it's a parabola. But it's not just one parabola. It's superimposition of many different parabolas. So I have a parabola like this, and I have a parabola like this. This one is much shallower, this one is deeper. The electron is going to be here, suddenly it gets excited somewhere else. Let's say at this level, this parabola goes like this, and this parabola is like that. The position of static equilibrium for this electron is in the other value. So this is one value, this is the other value. So electron, instead of going here, it's going to prefer to move here. It's going to try to interact with the lattice, and it's going to prefer to move here. This is called an intra-valley transfer. If it travels within that energy band, it's called an inter-valley transfer. So depending on that, we have different so now we look at mobility measurements. We have what is called as the Hall effect, where I have a magnetic field in the direction perpendicular inside the plane. I apply an electric field in this direction, Q equal to V cross B. Electron is the force, so V cross B is this way. So electron experiences the force in the vertical direction, hole experiences the force in the downward direction, and we have a separation of particles. The moment we have separation of particles, we have a built-in voltage. This can be used to determine the mobility of the carriers in the device. We have effective mobility, field effect on the mobility, saturation-based calculations. These are all different types of mobility models. I'm not going to go into every single one of them. For the different kinds of scattering events, I already explained those. So these are all the mobility models. We calculate mobility using these things. Again, every single one of these. Then we look at generation and recomposition. Photons get generated. Photons get absorbed. They excite the electron gets generated. So now, different types of generation are single step. There is a bound electron, photon interacts, kicks it out. That's one. What we have is we have a trap state in between. It excites the electron, but it goes to an intermediate state and then goes to the next. Then we have what is called the Auger. The Auger model is where the three particles are interacting. So an electron recombines in the hole, pushes an electron in the conduction band upwards, the energy of the equation. Or a hole gets absorbs certain energy from a different particle, gets excited to the conduction band, and then the energy is transferred, the rest of the energy is transferred from a different particle, which pushes it down the valence band. So we have three different types. So this is what it looks like. The that process, there is a photon from the electron into the conduction band. This is a this is inside the same value. This goes to a different value, like I explained previously. The Auger process. There are two electrons in the conduction band. One goes to the hole, pushes the electron upwards. There are two electrons in the valence band. One absorbs energy, goes to the conduction band. The other one gets pushed to the valence band. These are all the equations, not the total equations. We have impact ionization. There is a particle, it knocks off an electron from bound state. There is a vacancy. That's ionization. Basically, that's what happens. This is a Shockley Reed Hall, where we have an intermediate trap state. Wherever there is an excitation or recombination, an intermediate trap state is always there. This is called a Shockley Reed Hall organization. These are all the equations. So, that's it. Okay, so that's all I have for now. I'll hand it over to Kalayaran, who will pivot to a completely different field and talk about its application in our particular device, which is Spintronics. His work is actually quite interesting.
What is a spin? Actually, it refers that an electron, it's not only have charge also have a spin which is described in quantum mechanics. That the spin as an angular momentum. So it has an own charge, not only charge as well as it has a spin which has two states. In quantum mechanics, we see about the 5 numbers: principal quantum number, azimuthal quantum number, orbital quantum number, angular and spin quantum number. In that case, the spin quantum number, which from the Pauli principle also, they say that no two electrons have the same state. Like that, here also we have 2 different states. Which is one is a spin up and another one is a spin down. For the spin up state, we assume we can consider it as an anti-clockwise direction. So anti-clockwise direction which refers to spin up, and for the clockwise direction, the rotation of the electron which shows the spin down. It has a value of plus of and minus of. So for the electrons, I am going to say that having the spin. So how we can manage the spin in the devices? With the help of magnetism, we can manipulate the spin using the magnetic fields and the magnetic momentum and the materials which we are going to use. That will be discussed in the next slide. As we get in the magnetic moment, which is related to it through the spin angular momentum. When the magnetic field is increased, the angular momentum is also affected, so that we can manipulate the spin using the magnetic momentum. So that we properly representing the state and as well as the orientation of the magnet, which is the magnetic field. It explains that it has a relation, it is coupled with each other. Then we move on to what are the materials. There are types of magnetic materials like diamagnetic, paramagnetic, ferromagnetic, and very antiferric. These types of magnets. But which one we can choose for recoverable spintronic devices? For the diamagnetic and paramagnetic, as we can see, when there is applied field, they are not aligned with the magnetic field. Some of them, in diamagnetic, they are totally opposite. And in this case, paramagnetic, there is some slight difference. But for as you can see, the ferromagnetism, they are aligned as same as the magnetic field goes. So we are choosing these kinds of materials like ferromagnetic, antiferromagnetic, and ferrimagnetic, which are the magnetic field is applied, so that we can align the electron spin through the magnetic field. In case of the applied field, we can align both in the same direction using the magnetic field, so that we can manipulate the electron spin. Now let's go over how we can how this process is happen. For here, taking a ferromagnetic material, we have to see its domain and domain walls. A domain wall is nothing but a separating of multiple domains in a single domain. As you can see, each domain have its own aligned spin. As we before, this picture is a before and non-magnetic field effects. After we applying a field, all the opposite directions of every domains came into a single direction which is aligned with the magnetic fields. So that this is going to be happen when we keep this electron flow in the material. When the magnetic field is applied, all the electron will change its direction, like it's rotating its like own path. That's why it's having its own angular momentum, which is also explained in the Spintronic experiment. They have an experiment that electron's property so that it has 2 different properties that are seen in spin up and spin down. Then these are the energies. So the electron needs energy to spin. So what are the energies that we are upholding is spin interaction, dipole interaction, and the energies of crystalline anisotropy, which is from the changes. When the electron moves, can be accommodated with the crystalline anisotropy and the shape anisotropy and as well as the strain anisotropy. Then these are the equations, the LLG equation and LLGS equation. The under Snowski. Those are the scientists who form an equation that explains how the magnetic field and the electrons which are related with it and what we can do it in case of applying in a material type. So there's a little discussion on the equations. In this equation, just define not only the magnetic field but also its energies and the exchange energies of the interaction between the ferromagnetic layers and what are the things we are going to given. So it mainly focused on the rotation of the electron using a magnetization field. This is an updated version of the LLG equation. This is an LLGS equation. Spintronic and dampen, which is the advanced making the advance of this more equation. It is used for including in spin transfer torque devices. Which is a spin transfer torque. These are the devices which the electrons will interaction make it spin from one state to another state. Like we are changing their own original direction state to another using the magnetic field. Then let's we focus on the devices. Like these are the structures we can make using the spintronic principles. As you can see, they are all will be a tri-layer structure or multi-layer structure, having two magnetic materials, and in between there will be any barrier. Like it will be a non-magnetic material, or you can use an insulator also. So let's discuss more. What are the devices that we are using this spintronic applications? We have spin transistor, diode, and magnetic system for analysis memory, which is a memory devices. So mostly, basically, we are using spintronics. Mostly, we can see it on magnetic materials, which was very helpful for magnetic materials to read the data and make it faster to read it and write. In this magnetic, like I said, for the memory devices, there is a little structure called the MTJ, magnetic tunnel junction, which helps the electron to flow into the layer, like to make the ramp to work as fast and as well as to read and write the data. For this junction, I am going to explain about this structure is contained three layers. It is a free layer, fixed layer, and middle is a non-magnetic layer. For the free layer and the fixed layer, they both are the same ferromagnetic layers. We can also have different combinations of ferromagnetic layers, and we can also use the same magnetic materials. And in the middle layer, there will be a non-magnetic layer or an insulator barrier, which we can refer to. And in this configuration, as you can see, for the fixed layer, we will giving the current, so that the current will pass through the non-magnetic layer and then it goes to the free layer. Like I said, the current we are giving is a spin polarized current. When we apply a current to the ferromagnetic material, it will polarize the spin into the state which the ferromagnet is already in the directions. So as we applied it through the non-magnetic material, then it goes to the free layer, and that place, if the material is actually having the same direction, means it will allow. So it will be not like a very resistive type. It will be very low resistance. But in this case, it's an anti-parallel configuration, which will be one is going in one direction and another one is going in another direction, so that there will be a little more resistive to the electron flow, so that it will be as a line resistance, which we can take it as a logic of zeros and ones for the memory devices. And these two electrons are the insulating oxide layer also we can use it for the middle layer. It's like a sandwiching taking two ferromagnetic layers in between an insulating layer. These are the structure that is used for an ramp for the memory devices. For the single structure, this is the MTJ which we have shown before, and the top line is a bit line, and the line below is a word line, which will be using for the read and write process. And then the transistor is given for switching. When we want to read this, we want to turn on or off. Like we can use the transistor as a switch in this case. And this is an array of combination of giving more types, like giving a structured patterns for taking more number of bits. Here there will be maximum taking for 4 bits. Here will be taking for 8 bits. It will be multiplication, like for the magnetic memory accessing. These are the types of engrams we can produce through the spintronic applications, which we have already shown with the spin transfer torque. And here the spin orbital torque, it will be a little more advanced than spin transfer torque. Then let's move on to the semiconductor test, which I am going to explain about you. But for this one, photon things, which will focus as charge based, but in spintronics they are not only charge based, they also have a spin orientation. So here for a spin transistor effect, we will have these three major impacts, that is role going on for spin injection, spin transfer, spin reduction. Spin injection may occur in this portion when we apply a current to the source, that will be a spin polarized current. It will inject inside the channel, which is the semiconductor channel we are getting. Maybe we can use the GaN as well as the semiconductor channel. As it is travel through channel, the spin has a lifetime, so it will not keep the spin as long as it travels through a larger area. So when we need to control it or manipulate, we will give a current bias through the gate, and it will have a reaction to that spin will be turned. This effect is defined by the Raspa spin orbit interaction effects. That's called the spin Raspa effects. That will define how the spin is manipulating inside the semiconductor channel. Then after the spin is effect has happened, then the detection will be on the drain area, whether the spin direction is having the same as the drain, so it will allow, or else the repulsion will be happen. So it will be like, it will also use as an on state or off state. Like when it passes through the drain, it will be in on state, or otherwise it will be off state. So this is how the spin transistor spin effect is called, based on spin. And the advantages is that the low power consumption is a non-violent memory for memory devices, and the switching will be very fast comparatively to the conventional